So section 2 is momentum and the impulse momentum theorem. So yesterday, remember, we saw impulse was capital J, and the units are kilograms times meters per second. So today we have formulas that we're already aware of, like F equals ma. Acceleration is change in velocity over change in time. We're deriving this equation here. The average force times delta time equals mass times final velocity minus mass times initial velocity. So the left side of the equation is impulse, right? We saw this yesterday. So we'll use the letter J for that. And it is a vector, remember, the direction matters. So the right side is the change in the quantity mass times velocity, right? So like we would have mass, if I factored out mass, we'd have V final minus V initial. That's just delta V, okay? So that's what that's talking about there. So this quantity, the product of an object's mass and velocity, is the momentum. So that's a new word there. And the letter we use for momentum is P, and it is a vector because velocity is a vector. Delta V would be a vector. What direction are we going? So we have P as a vector as well. So P is mass times velocity.
So
Okay.
wouldn't that also equal impulse? Because isn't the velocity, isn't that the same?
Is that impulse?
No.
So if F average delta T up here is impulse, and down here we have mass times velocity is momentum, right? But we have, this is really the change in momentum then, if you think about it, right?
Yeah.
Then would this be impulse here? It wouldn't quite be. Why'd I do that? Okay. It wouldn't quite be, right? It would almost be. We'll get there. Okay. So it would actually be, we'd have to have a change in momentum.
Which I'm assuming was something like that.
Yes. Okay. So we have momentum equals mass times velocity. So it is a vector that can be decomposed into x and y components like we've been doing pretty much all year. And it points in the same direction as the velocity, which means the components have the same signs as the velocity components, which is great. So we have these guys. Momentum in the x direction is just mass times velocity in the x direction. Momentum in the y direction is mass times velocity in the y direction. So that's pretty easy to work with. The units of momentum are mass, so kilograms, times velocity, which is meters per second. That should sound familiar. Kilograms times meters per second was what we were talking about yesterday. So I'm starting to answer your question. That sounds kind of like J, which was impulse, right?
Mm-hmm.
Okay, so now we have the reason for the unit preference for impulse. It was to match the units for momentum. So a heavy, fast-moving object will have a huge momentum. Think of a train. That is a heavy object. If it's moving fast, so not when it's like coming to a stop in the train yard, it has an enormous momentum. It takes a lot to get that thing to stop. A light, slow-moving object has very little momentum. It's super easy to get that thing to stop. However, a light object moving fast can have the same momentum as a heavy object moving slowly. So what would a light object moving fast be, maybe?
Like a motorcycle going 120 miles per hour.
Is a motorcycle a light object?
A baseball going 120 miles an hour.
Something maybe even lighter than a baseball, moving even faster.
A paper airplane. A photon going the speed of light.
Okay, how about a bullet?
Yeah, that sounds good.
Okay. Yeah.
Okay, so the impulse momentum theorem then is this. Now J is the what?
Impulse.
Impulse.
So the average force times delta T also.
And then P is the what?
Momentum.
Momentum. And so P sub F minus P sub I would be the change in momentum. There you go.
Oh, no.
Now your question is answered. So this is change in momentum. Excellent handwriting. Change in momentum. So P sub F equals MVF, and P sub I is MVI, and P sub F minus P sub I is delta P. That's the change in the object's momentum. So basically what we're saying here is the impulse that's delivered to an object causes the object's momentum to change. So an object is moving along a straight line, let's say, as it moves in some direction. Now, I deliver some impulse to that object, and it doesn't matter what direction I deliver the impulse to that object in. So whether it's to the side or frontal impulse or from behind or whatever, that is going to change the object's momentum in some way. And that's basically what this is saying, okay? So another way to write this theorem is here. Momentum final equals momentum initial plus the impulse that is delivered. And these are all vectors. So the direction of the final momentum is going to depend on the initial momentum's direction plus whatever the impulse direction was. So the theorem written in component form looks like this. So I have, it's basically the same for both the x direction and the y direction. So if we're only working in one direction, we only have to worry about one of these, but usually we're going to be working in 2 dimensions in the real world. So you do need to know both. Actually, in the real world, we're working in 3 dimensions, but for us, it's just 2. So we have the impulse is equal to the change in momentum, which is momentum final minus momentum initial, and that's going to boil down to these guys over here. Mass times velocity final minus mass times velocity initial.
If we wanted to, we could break it down even further and go velocity equals delta x.
Yes, we could.
It's
Yep.
like a giant skeleton equation.
Yeah.
The key concept.
So we have this important idea here. The impulse causes a change in momentum. So I was kind of talking about that already. The putter delivers an impulse to the golf ball, changing its momentum. So initially, the golf ball from the left side of the picture is at rest. We see that the momentum initial is 0. So it's just sitting there. Now the putter comes through and strikes the golf ball. Okay. And we know that putting, hopefully we know that putting is a more gentle strike on the golf ball. So we are applying this gentle hit on the golf ball, but it does give us this impulse on the golf ball in this direction here. So now we see that the golf ball is going to have a final momentum, and that means that it has a final velocity. Okay, so it had initial velocity here with a momentum of 0. The initial velocity then was also 0. Now we have a final momentum here, which means that we have a final velocity associated with that momentum. Okay, whatever that is, right? Now, the initial velocity was 0. The final velocity was whatever it is because of the impulse that was delivered to it. Okay, so in this case, initial velocity is 0. The formula ends up here. The putter delivered an impulse to the ball, and then from there we can solve. And if we were asked to find the final velocity, if we knew the impulse that was delivered, we could certainly do that.
So the impulse is equal to the
Mass times the velocity. Right?
In this situation with the initial velocity of 0 and so on, yes, we can, if we know some information about the mass of the ball and so on, we can solve problems. And that is the power of the impulse momentum theorem that we're working with. This is a new way to solve like final velocity type of problems that we were working on in the more towards the beginning of the year. These types of problems can be solved in a more efficient way, really. Okay, so as you'll see here. So on a situation like this now, we have the soccer player. So the soccer ball is coming down. I don't know if it's super clear in the picture, but the soccer ball is coming down, and the soccer player is going to do a header on the ball. Okay, so the head delivers the impulse this time. to the ball. So now the impulse is delivered in this direction, and the ball is going to turn and go off in some other direction. Okay? So now the impulse is delivered and the ball has a momentum final. So the initial momentum was in this direction with the blue arrow, and then we have the final momentum in this direction. Notice it doesn't recoil in the picture. It doesn't necessarily have to like recoil back equally opposite the direction it was coming from. It depends on the angle of the impulse in the first place. Okay, so breaking these things into components and then using the component form is going to be important. So we have the initial momentum with this component here. We have the final momentum, or we have the impulse being delivered along this vector. So now the vector addition gives us the final momentum vector. Okay? So the vector addition that we were doing earlier in the year allows us to come up with the final momentum vector there. Using a graphical approach there makes it kind of an easier way to analyze how this ends up. So we have initial momentum is not zero. The motion is not solely along the x-axis. So vector addition was very useful to find the final momentum, breaking the vectors, momentum initial, and the impulse into components, and then adding them mathematically would be the other approach. Okay.
So since this is a vector, we need to figure out like the degree. It would be.
Yeah, so we would find the degree as well. And so then the mathematical approach, breaking the components into, or breaking the vectors into components would be the other approach. So let me just show you how that would work. The initial momentum vector would have an x component that way and a y component this way. And then let me pick a different color here. I'll go with this one. The impulse vector would have an x component this way and a y component this way. So now we're just going to add those components. So we have the x component going this way, and then the x component from this one going this way, and then the y components for the initial momentum vector. So here we are at the end here going this way, and then the y component for the impulse vector taking us this way. And then from where we started to where we finished, the resultant vector, and I'm not really drawing these to scale, but here's where we started and here's where we finished. So here's our resultant vector. Okay? So that's how you do that, kind of more mathematically. Of course, we would have the numbers for those, and then we would calculate it that way. And then the resulting angle would be that angle right there. Okay? All right. So then we think about this one. The puck, which is seen from above, was moving with initial momentum when it received an impulse J from a hockey stick. So like the puck is sliding across the ice and it has some momentum. Now a hockey stick hits it, giving a final momentum. So using our ideas that we've seen, which arrow best represents the puck's initial momentum? So we don't know the initial momentum. We got to figure it out. So let's see what we think. So we have to think about what it had to be in the first place here, plus this guy, in order to wind up with that as the result, right?
Vector subtraction.
Oh, okay.
So what could we have had in the first place to wind up going in this direction here?
It has to be one of the vectors the answering vector has to be going up.
We have to have some sort of up component, right? We have to, in order to wind up going up, because this guy is purely to the right, okay? And this guy has some right component to it. So we must have some sort of up component in the first place in order to be going up in the end. Agreed? Okay. So A has no up component. It just has pure right. If we were pure right and we gained more pure right, we'd just be going pure right but more, right? So it can't be A. B has some down and left. Well, the J here would have wiped out the left part of it and we'd be going down instead. So we can't have B. C would have had left and then the impulse went right. So we just have some left or some right. We don't know. with no up though, for sure, right? So it can't be C. And then if I look at E, E has some left. No, I'm sorry. E has some right. And then the impulse to the right, but it also has some down. So we're going to the right, but also down. Okay? So it can't be E. D is the only one that would make sense. It has some component to the left, and it has some component up. Now, the impulse J to the right would wipe out the left component, we think, but the up component would give us the up and right that we're looking for. So the answer must be D. Okay? That's the only one that makes sense. It's the only one that gives us the up component that we're looking for. Make sense? Okay. So that's how that one works. And really, an analysis like that is the only way that you can do a problem like this. Okay? So a ball of mass M equals 0.25 kilograms, rolling to the right at 1.3 meters per second, strikes a wall and rebounds to the left at 1.1 meters per second. So we take a minute to visualize what that looks like. First, I'm going to define axes. So we have regular axes. We're rolling to the right at 1.3 meters per second. So I'm going to define positive x as to the right. Okay? Now, positive y we could call up, but in this case, positive y might be like if I laid down my axes so that rolling to the right was positive still, but then if this bounced off the wall and came off at an angle, I might want to define positive y as coming off at an angle, to the right or to the left relative to the wall. You know what I mean? So that the angle to the left was positive or the angle to the right was positive. So laying down the y-axis might make sense. In this case, up positive is fine, okay? Because it doesn't matter. It just comes straight off the wall. So strikes the wall and rebounds to the left at 1.1 meters per second. So when it comes off of the wall, the velocity there, the speed, is actually going to be
Less.
not less. I mean, that's pretty obvious, right? But
Well, it's going to be negative.
Negative, yeah. So that is actually negative 1.1 there, okay? So we got to remember that. Now, what is the change in the ball's momentum, and also what is the impulse? So the change in the ball's momentum, we're looking for P there, P final, right? P initial, P final, so we're looking for delta P in the end. And then what is the impulse delivered to it by the wall? We're looking for J there, right? Okay. So we need a before and an after. So in the before, the ball is moving to the right. So like in my mind, I'm thinking, okay, before the ball is moving to the right, we have momentum initial. So P sub I equals mass times velocity initial, right?
Yep.
Okay. So the mass we know is 0.25 kilograms. And the velocity initial was 1.3 meters per second. Okay, very straightforward. Multiply that out, and we got, I'll just do it, 0.325. Yes. Kilograms, meters per second. Okay, now in the after. Okay, and that is the ball is moving this way now. So this is momentum final. So P sub F. That will be mv sub F. The mass is still the same, 0.25 kilograms times thank you, negative 1.1 meters per second, because we're going against positive x. So this time we get negative 0.275 kilograms meters per second. Okay, so now the first question says, what is the change in the ball's momentum? How do I calculate the change in the ball's momentum?
P final.
So delta momentum equals momentum final minus momentum initial. Well, momentum final was negative 0.275 minus 0.325. So what is this? Looks like
Point.
negative 0.6, yeah. Negative 0.6. Is it just 0.6? We got two significant figures, negative 0.60 kilograms meters per second. Now, the second question, what is the impulse delivered to it by the wall?
That's going to be equal to 1.3 minus 1.1 because the
Well,
impulse
it's
stays positive.
Negative 0.6.
Because what is impulse?
It's that.
J equals
delta
delta P
P.
equals negative 0.60 kilograms meters per second. They're the same thing. When a car gets into a crash, the car goes from moving to standing still very quickly, as do the driver and the passengers in the car, hopefully, if they're wearing their seatbelt, right? There is a change in momentum then. This is unavoidable. What strategies have we developed in vehicles to help reduce the chances of injury?
Airbags.
Okay, airbags, what else?
Seatbelts.
Seatbelts.
Brakes.
Okay, so we collided with something, right? So the brakes didn't help. We tried, but we did collide. So the brakes are not going to count here.
The frame.
Okay, what about the frame?
The way they build the frames nowadays, they make it whereas the stuff that is coming your way doesn't collide with you.
Okay, so like the steering column is now collapsible. The frame is collapsible. So like the accordion, you know, when you see the crunch, it collapses down on itself rather than
shoots the engine under.
Yes. So collapsible. Let's say collapsing parts. So that'll encompass all of those things. The frame, the engine, the steering column, those things all collapse in ways that keep the driver and the passengers more safe. Those are great examples of how cars have become more safe to try to protect the passengers. Of course, the passengers have to still protect themselves by wearing the seatbelt, keeping the airbags on, right?
Imagine having a vehicle with airbags.
Not sitting too close to the steering wheel and stuff like that. So, yes, wearing the seatbelt properly is another one. So there you go. Lots of safety features have come into place in the newer vehicles. Not driving too fast in the first place, stuff like that. So there you go. In the example of a car crash, the vehicle has momentum, P sub I, just before impact, and zero momentum, P sub F.
Right after.
The impulse momentum theorem tells us that J, the impulse, equals the average force times delta T equals delta P. And so that's P sub F minus P sub I. And since P sub F is 0, that would just be negative P sub I. So if we arrange all of that formula, we will get the average force equals negative P sub I over delta T. Okay? So this implies that the average force needed to stop an object is inversely proportional to the duration of the collision. So if the duration of the collision can be increased, the force of the impact will be decreased. Okay? So all of these things that we have just talked about, the seatbelt, the airbag, the collapsing frame, all of those things are doing what?
Extending the collision.
They're extending the length of the impact. Okay? They're extending that duration. And that is creating a decrease in the force of the impact. And that is helping to save lives. Okay? So anything that we can do to increase the delta T for the impact is helping to decrease the force, and that is what is saving lives. Okay? So whatever it is, increase the delta T to help save lives. Okay?
You should put that on a poster. Increase the delta
Increase
T
the delta T.
to
Yep.
save lives.
So that's how you protect to keep things like the human body intact
Inside
to save
still.
lives. So later when we do the impact project, you're trying to increase the delta T to save the life
Of
So-
an egg?
of whatever it is.
So like then, if you're fatter, is that going to increase the impact?
So I guess potentially, yeah.
So it's not such a bad thing to be fat.
Yeah, maybe not. No, that's untrue. Because
You have to deal with like cholesterol.
No, yeah.
Hey, but at least you won't.
Okay, so the seat belts in vehicles are made of webbing that is designed to have a significant stretch when supporting large forces. Why is this useful?
So they don't tear.
Okay, maybe they don't tear.
It allows more time for you to go out.
That's right. If they are more elastic, they will stretch more when they are under a
Duress.
large force.
Okay, but then why do they have it where you slam forward, the seatbelt locks?
Because they don't want you to go too far. If you're just going
You don't
forward
wanna
and
bash
forward
your
and
face on
forward,
the steering
then you're
wheel.
just going to hit your head off the windshield or the steering column or the steering wheel or something, right? But so they lock, and then you're still going forward, and they are stretchy. Why?
So they're just, it's kind of like a,
Because now you gain like an extra 2 milliseconds.
it's like in those
Yes,
cartoons.
it gives you an extra 2 milliseconds or 5 milliseconds or something of duration of impact. Okay, and that is the whole point, to make the delta T longer, which reduces the force. Oops, what is that? Which reduces the force of impact. It doesn't matter how much longer it is, as long as it is longer, it reduces the force of impact. All of these things combine, and they reduce the force of impact, even if it's just a little bit more.
Now you make me scared to drive my truck because it doesn't have airbags.
Yeah, the older vehicles.
Yeah, it don't got no airbags.
Yep,
and the
if you-
seatbelts don't stretch. I can tell you that much.
So you drive the older vehicles, you don't have these technologies that are in the newer vehicles now, and it's a risk.
But they're made out of pure metal, so like needless to
Pure
say-
metal?
They're
Pretty
not
much.
going to collapse.
Yeah,
So
Yeah.
that's going to.
So they do have that going for them, but they don't have the collapsing, the accordion, frontal impact stuff.
oh yeah, that's
You
why
know,
you'll get the drive shaft.
They don't have the side curtain airbags and those things. And those technologies do save lives for sure.
Yeah.
So
Be like
okay,
that gal that stuck rocks on
total momentum.
What?
the gal that put rocks around your steering wheel to make it more like
Pretty.
aesthetic.
So
Killed herself by banging
All right.
her hand on us?
if more than one object is moving, so we have a system of objects, then the system overall has an overall momentum, and that's called the total momentum. And so we have capital P. This is a vector, is just the vector sum of the momentum vectors of all of the moving objects in the system. Pretty straightforward. We've done this before, total torque and so on, right? Total net force and stuff like that. So we have several objects. These are like billiard balls, pool balls, okay? So we have several objects moving on the pool table. We have a total momentum then, okay? So we have all of these vectors here being added together. The total momentum would be the sum of the momentum of each of those balls together. Pretty straightforward. Okay? Good? All right. So not much more to say about that. Take a look at this. The cart's change of momentum is what?
What do you mean?
So if we call positive to the right, then what is its momentum to start?
Negative 20 kilograms.
So 10 times 2 is 20, but it's moving to the left. So this is negative 20. What's this one?
Positive.
10.
It's still the same 10, but it's moving to the right this time.
Yeah.
So 10 times 1 is 10, and it's moving to the right, so it's positive 10. Now, how do I calculate the change of momentum is final minus initial? So it would be 10 minus negative 20. The answer is F.
Forgot about that.
Yeah.
Double minus.
You got to go final minus initial. So 10 minus negative 20 is positive 30. Okay, so that's it, right?
Yep.
Okay, not too bad.